So first of all, thank you very much for letting me give this talk. I know it's Friday, so my talk is going to have a lot of pictures in it, not a lot of formulas or numbers. I'm going to be talking about the work that I've done with my advisor, JJ. It's based on a paper that we put out on the archive a few weeks ago, and it's entitled Loop Level Double Copy for Massive Quantum Particles. And essentially what we've done is we've bootstrapped amplitudes with massive scalars at tree and one loop level. So three sort of cool things that we found that I just want to start by mentioning are, first of all, that at tree level, it's completely enough to use color kinematics and factorization to determine these tree level amplitudes with massive scalars. And we've also found a color dual representation at one loop with massive scalars. And also here, it's enough to use color kinematics and unitarity to determine these amplitudes. And these kinematic weights that we find can be used to address massive scalars both in an adjoint and a fundamental representation. So why is it hard to calculate gravity with traditional methods? I'm sure this is known stuff to a lot of people here. Certainly two of the problems is that off-shelf Feynman rules give us very large and unwieldy expressions. And we also get a very large number of graphs as we go to higher multiplicity and higher loop level. So this is why we've tried to bootstrap this type of calculation using two concepts or two insights. The first of these is the color kinematics duality. And what this allows us to do is it allows us to write this large number of graphs in terms of a smaller set of basis graphs. And it also means that if we build something that satisfies the color kinematics duality, we can deal with amplitudes in a gauge theory, then double copy them to get the gravity results. Now we've also used unitarity methods, so factorization at tree level and unitarity cuts at loop level, because then we can write things in terms of easier on-shell expressions. So today I'm going to start by talking about the color kinematics duality in a very sort of graphical based way and try to show you how we've used that to build our graph weights. Then I'm going to talk about how we've built stuff at tree level, and then finally our loop level results. So the color kinematics duality. I don't think it needs a very long introduction here. Maybe it suffices to say that it was initially established in the adjoint representation, and now it exists in all sorts of theories and representations. And among these is massive scalars in the fundamental. So that's what we'll be using today. So what is the color kinematics duality? Now, if you just start by looking at this expression for general L loop amplitude, I don't want you to get too distracted by this full expression. So we're summing over the cubic graphs that contribute. We're integrating over the loop momentum. The part I want you to focus on is how we're dressing the individual graphs. So I'm just going to use a simple example to go through these. So we're dressing with a kinematic numerator, a color factor, and a propagator structure. Now the propagator structure of this graph is easy. There's only one propagator and it's massless. The color factor is also fairly easy to read off. In this case, we have a cubic purely gluonic graph. So this just gives us two structure constants. And these structure constants obey the Jacobi relations, which we can write in terms of graphs like this. You see that we've moved the indices around. Sorry, the external legs around. Now, the tricky part, or the thing that it's not easy to read off the graph directly, is the kinematic weight. So we've used a functional kinematic numerator, which means that every graph topology or graph type gets its own function. And the arguments of this function are the external legs of each graph. And for the loop case, we also give the loop momentum as an argument. Now, for this to obey the color kinematics duality, we want it to obey the same Jacobi-like relationship as the color factors. Now, color factors also obey anti-symmetry, which means that if we take this 3-point vertex, we can dress it with a structure constant. And if we flip A and B, this gives us a minus sign. So we're going to want to impose the same type of anti-symmetry for our kinematic numerators. Now, sort of to summarize, we're going to want our kinematic weights to be functional numerators that obey the same type of algebraic relations as the color factors. Now, I've only showed you this for a 4-point gluonic example because it's an easy example to show. But of course, we want this to be true for any subgraph of a larger graph. So if we take this general graph and we look at one of the internal edges, we can think of this as an S channel. Now, if we change the connectivity and turn it into a T channel, that's what this T hat operator does. And similarly, we turn it into a U channel. We want these three graphs to obey the same type of relationship. So this Jacobi-like relationship. Now, this is probably familiar to a lot of people, and this was just the massless case. So how do we deal with the massive particles? In our case, we've introduced mass using this vertex. So we have a gluon and a massive line going through, and we're going to address that with some generator. The generator gets an adjoint index from the gluon and two indices from the massive line. Now, how we treat this from here depends on whether we want to treat this as a fundamental type particle or an adjoint type particle. And by fundamental type, I mean that we're distinguishing between a particle and antiparticle. So we have something coming in and something going out of the vertex. Then it would also be natural to give a bar to one of these particles to distinguish which one is which. If we treat this as an adjoint type particle, we're not really distinguishing between particle and antiparticle, so we'll just give them indices ij. Now this is going to matter when we write down ordered amplitudes, but I'll get back to that later. So in either case, it's very convenient to introduce some antisymmetry. So when we flip I and j, the two particles, we're going to want a minus sign. So we introduce these sort of artificial generators where flipping I and j gives us a minus sign. And this is perfectly okay for us to do because anytime we put this into something that we care about, like an amplitude, the two minus signs are going to cancel because we're introducing this in the color factor and in the numerator. Now we're going to want a Jacobi-like relation for this type of graph. Now this is really just the commutation relation between these generators. Where it gets a little bit different if we choose the adjoint is that we can introduce a third sort of optional Jacobi-like relationship. So if you look at this 4-point graph with two massive scalars of same mass, if we don't care about particle-antiparticle, we can introduce this third type of relationship, which you can write down using the Fierce identity and using this antisymmetry that we're introducing. Now this you could not introduce for a fundamental type particle because then you would have vertices with particles and antiparticles and antiparticles. Now, as it turns out, the kinematic weights that we find do obey this third Jacobi-like relationship, and we can use those weights for both adjoint type and fundamental type. But again, I'll get back to that a little bit later. So just to summarize, we have these two parentheses 3 relationships that we want our kinematic numerators to obey. So then we can start the construction. We're going to start the construction at sort of the lowest level, so just the 3-point amplitudes. We have 2 of them, and in each case, there's only one graph topology contributing. So each of these gets its own functional numerator. And again, you see that the arguments are just the ordered external legs of these graphs. Now this functional numerator gets an ansatz that consists of kinematic products. So when we have external gluons, we get polarization vectors here. And of course, we get the momentum of the particles. So we get the same thing for this massive type of amplitude. And for the 3-point case, it turns out that if we just impose all the antisymmetries that we want, so like I showed you before, flipping, exchanging K1 and K2 should give us a minus sign, this is determined up to an overall constant. And this overall constant we can set to be sort of whatever we want. You could set it to be the coupling, or you could set it to be 1, which is what we'll do here for simplicity. It just depends on how you're defining your amplitude. So we'll get to an example that's a little bit more interesting. Here's a 4-point amplitude with 2 massive scalars of distinct mass. That's what the red and blue means. And now we're not allowing particles with distinct mass to talk to each other. So we're not allowing vertices with both masses. So in this case, this is the only topology that shows up. So we give it this functional numerator that gets this ansatz. And in this case, all the external particles are scalars, so there are no polarization vectors. Now, Most of these coefficients are determined using the anti-symmetries of this graph, and we're left with an overall constant. And this overall constant is determined using factorization. So we sort of cut this propagator and we compare the state sum over these 3-point amplitudes, which we already found, to dressing this graph. And here, of course, we've cut the only propagator that we had, so there's no denominator. We have our numerator function and we're imposing the cut conditions. So imposing this fixes this last coefficient and gives us this amplitude. And now we have an example where we actually get to see color kinematics. So this is the 4-point amplitude with one massive scalar. And in this case, we actually have two distinct topologies. So we have one with a massive propagator and one with a massless propagator. So each of these gets its own functional numerator. However, if we write down the color kinematics relationship between these graphs, we see that we can actually write the massless guy as a linear combination of the massive guy with the arguments moved around. So this has become sort of our basis graph for this amplitude. And what this means is that we only need to give an ansatz to this massive guy because the massless guy is then determined by that. So we give this an ansatz. In this case, we have two external gluons, so you see that we get some polarization vectors. And then we use the symmetry relations and all the Jacobi-like relations that we can write down between these graphs to determine most of the coefficients. Again, the final coefficients are determined using factorization. And in this case, we have two propagators, so we do two factorization channels. And this allows us to determine this functional numerator. And again, the massless one is just a linear combination of this. So what we see that we get is this sort of pyramid scheme of graphs where we start with our 3-point amplitudes that are completely determined by anti-symmetries. And then we propagate the information from these down into higher multiplicity graphs using factorization and the color kinematics relationships between the graphs. So we've done this at least up to 6-point. And the reason why we didn't go to higher point is that we really wanted to look at loop amplitudes. And this is what we wanted to build the loop amplitudes. So now we look at construction at loop level. Now the construction at loop level is very similar to the tree level one. We can even look at the same amplitude. So we consider this amplitude with the two massive scalars of distinct mass. And we can write down all the topologies that contribute to this graph. Now, I'm not including tadpole graphs, essentially because our motivation for doing this was to eventually take the classical limit. So we haven't taken too much care with those types of graphs. Now we want to reduce this down to a smaller set of basis graphs. And for that, we use the color kinematics. But what does it mean to use color kinematics at loop level? So this is what I mentioned a little bit before. If we take this box graph and we look at one of the internal edges, we can think of this as a T channel. Now, if we again change the connectivity of this graph, we sort of clean up the expression that we get, we see that we can write this triangle graph as a linear combination of the boxes with different orderings. Similarly, we can take this other internal edge and do a similar procedure, and we see that we can write this bubble graph in terms of triangles. And this is probably familiar to some people, that we can write the triangle in terms of boxes and the bubble in terms of triangles. So essentially, for these three graphs, we see that the box graph is a basis graph. Now, if we write down all these relationships between the graphs that we can, we end up with just two basis graphs. So this massive type of triangle graph acts as this massive bubble. So we determine a lot of the coefficients using the symmetries of these graphs. And again, all the color kinematics relationships that we can write down. And the final coefficients are determined by a spanning set of cuts, two particle cuts. So we see that we have one massless cut, one massive cut with two distinct masses crossing the cut, and one massive cut with the same mass crossing the cut. And these are ordered cuts, which means that we have ordered amplitudes. But what does that mean for this case when we have same mass particles? So we take a closer look at this cut or this amplitude. Now, what this ordered amplitude means depends on whether we choose the adjoint type or the fundamental type representation. In the adjoint type representation, this ordered amplitude gets a contribution from the S channel and the T channel. So this is just the numerator with the propagators. However, if we treat this in the fundamental type, these are actually two different ordered amplitudes because they have different color factors. But as you can see, this adjoint type ordered cut is sort of built up of fundamental type building blocks. Additionally, if we treat this as an adjoint type particle, we get this third Jacobi-like relationship that I mentioned before. Now, as it turns out, we can impose this third Jacobi-like relationship, and we get kinematic weights that obey both the adjoint type cuts and the fundamental type cuts. So we ended up doing the adjoint type cuts because there are fewer of them. So we move on to 5-point. The 5-point case is also similar to the 4-point case, except of course we have another particle, so we get more of everything. In fact, if we write down all the topologies for this theory, not including the tadpoles, we get 33 distinct topologies. And again, writing down all the color kinematics relationships between these, we can reduce this to a basis of just 6 graphs. And just to illustrate how much work we're saving ourselves from, if we were to give each of these 33 topologies its own minimal ansatz, we would start out with around 10,000 parameters. And just reducing this down to the 6 basis graphs, we start out with less than 2,000 parameters. So this is saving ourselves a lot of work. Now, again, we're fixing the final parameters on a spanning set of cuts. This again looks a lot like the 4-point case, except we get this new type of cut with one mass particle and one massive particle. And you see that in this case, we have 2 cuts with same mass trees. And we find that at 5-point, we get the same result as at 4-point, that we can satisfy both the adjoint type cuts and the fundamental type cuts. So now we can add this 1-loop layer to our pyramid. So we started out with just these 3-point amplitudes. We propagated the information from these down to higher multiplicity tree graphs using factorization and color kinematics. And we see that we can actually even propagate this down to the 1-loop level using unitarity cuts. So since what we've made is by construction color dual, it's quite trivial to take the double copy graph by graph to get the n=0 supergravity coupled to our massive scalars. However, the n=0 supergravity, in addition to the graviton, has this massless scalar and possibly this anti-symmetric tensor. And what we really wanted was the pure gravity result. So what we've done is use the method of maximal cuts to project out these excess states. And we're hoping to put that out fairly soon. So some of the future work we would like to do is see if there's a way to double copy directly to pure gravity, not via these maximal cuts. For example, by introducing some ghostly matter in the initial theory. We would also like to generalize to higher spins for massive particles and use the results that we already have and generate some classical observables. And of course, extending to higher loop orders. So starting, for example, with 4-point 2-loop. So I just want to finish off with a sort of a recap of the cool things that we found. So at tree level, these massive scalar amplitudes completely determined using factorization and color kinematics. And there is also a color dual representation at 1-loop level that can also be determined using color kinematics and unitarity cuts. And these kinematic weights that we find can be used for massive scalars in both the fundamental and the adjoint representation. So that's all I had to say. Thank you.
Thanks. Very clear, super. Any questions? Ollie, fast on the draw.
Thanks for the really beautiful presentation. I was wondering, did you look a lot at linearized gauge invariance as a check, or did you consider putting it into your criterion list?
So gauge invariance of the numerators?
Exactly, sending the polarizations to the respective momenta.
Yeah, so actually first that was one of sort of our the things that we were imposing to determine the coefficient.
Uh-huh.
But then we actually found that this combination of the factorization and color kinematics gives us gauge invariance. So yeah.
Is it more like an observation, or did you start cooking up a general reasoning?
I'm not entirely sure. Maybe JJ has a better answer to that. Or maybe
Hi,
he
sorry,
went somewhere.
I just lost net connection, but I'm in on my phone. So I think this hasn't been proven to all multiplicity, so you can treat it as an observation through the tree level amplitudes we calculated. This is, I believe, we should check with Lorenzo. I believe there's a pretty sharp argument for pure Yang mills that factorization color kinematics gives you gauge invariance.
Good, thanks a lot.
Okay, Enrico.
Yeah, so I have a kind of related question maybe. So there are these bubbles on external legs, and are you claiming that imposing color kinematics duality and a cut, only cuts where you're not having this bubble on external leg cuts fixes all degrees of freedom? Or are there...
Sorry.
So is that differently? Do you get the UV structure of these amplitudes correct without imposing anything else?
So yeah, so that's correct. So we did these true particle cuts, and you're right. We don't access the. So we've been calling them snail graphs. I'm guessing that's what you mean. So we don't access those, and we don't access the tadpole graphs. And we haven't really gone further into that because eventually what we wanted to do was take the double copy and then the classical limit. So then those graphs wouldn't really be relevant in that scheme. But of course, if you wanted to do something, or if you wanted to take the QCD result, you would have to look into that. But we haven't yet, but it would be interesting to see.
So just to clarify, you don't get the UV correct without doing these additional checks.
I'm not sure.
Thanks.
And maybe I can exercise my chairman's privilege to squeeze in a sort of related question. Is it possible to impose as a constraint that all the tadpoles are zero, say, and still arrive at a set of solutions?
We tried that, and at least, so if you set all the tadpoles to zero, you don't obey color kinematics.
Okay.
So I guess the short answer is no. You
Yeah.
can minimize the UV behavior of some of the tadpoles. So I think I'm thinking of snail graphs. Because we didn't write down the tadpoles, but it's a similar thing. So we tried to minimize the UV behavior of the snail graphs, and you can do it for a subset of the graphs at a time.
Mm-hmm.
So I think you could do it for like 5 of 9 snail graphs at a time. But we ended up not including that in the resulting numerators that we put out.
Yeah. Okay.
But I guess the short answer would be no.
Yes, that's right. So another question from Carlos.
Hey, yes. Have you tried? Yeah, I guess a very simplest case, 8 points, 8.3 level with all external quarks. I'm not sure if.
No. So the highest I know we went to 6 point. I'm actually struggling to remember if we tested 7 point. But we had not tested 8 point.
Right. I mean, my understanding was that some people have tried.
It should be completely doable.
Right. My understanding was that people trying to compute this weren't able to solve it. So I'm not sure if you can either prove or disprove that this can be done. Would be interesting.
Oh,
probably,
well, I guess
it's
it would
probably
be interesting to see. Did you say they were quarks?
Yeah, 8. Yeah.
Because these are scalars.
So 4 quarks
were a little bit different.
Right. So I guess 8 fundamental particles external, and then there's some gluons.
Yeah.
in the middle, I
Yeah.
guess.
So
So yeah, I think
it's
it would be an
possible
easier
that, so
check.
the fundamental type representation, I guess, would be closer to
Mhm.
something with quarks, but then the
Yeah.
actual expressions, of course, would be different. But
Sure.
it might be interesting to see. Yeah.
Okay, well, let's thank Ingrid again.
Thank you.